Alright y'all, I am back with another repair video. You guessed it, that's pretty much all that I do on this channel. But it's going to be something a little bit different than what I've been doing. Now, I've mentioned this before in other videos, but if you're new to my channel, I am a lab instrumentation engineer. That's my title at a biotech company. And so I'm responsible for maintaining all of their lab equipment. We got about 400 pieces of equipment here, variety of different kinds, and it's my job to maintain them all. Let me just preface, I am getting over a cold, so if I hear any coughing or sniffling, I apologize in advance. But yeah, so this video is going to be on a work-related piece of equipment that I've been struggling with, and I think I finally got it fixed. But yeah, so a bit of a background. So one of the biggest challenges to my job is the repair prevention strategies that the manufacturers of this equipment employ. And that could be anything from refusing to sell parts, not providing service manuals. They'll give you a user manual just so you know how to use the equipment in a normal operation, but no service manuals. In those user manuals, there's very little about troubleshooting or repair. Sometimes there's even very little about preventative maintenance. Definitely no electrical schematics. I would say for about 90% of the equipment I have no schematics. But yeah, there's just a variety of different tricks that they employ to force you to go to them to fix it, because that's a big market for them. So that's, like I said, that's the biggest challenge to my job, and it definitely came up with this repair. So this is a Molecular Devices. That's the company. Molecular Devices SpectraMax ABS Plus, and it is a spectrophotometer that can read microplates. Biotech, it's referred to as a microplate reader, and these are plates. So biotech scientists will use these. This is a 96 well plate. They'll culture cells. They'll aliquot them into these plates. They'll mark them with a fluorescent marker, or they'll do a variety of different things to analyze the cells or whatever they're working on. We also do antibody characterization and development here. So yeah, that's usually what they're using. That's the main consumable that they will use to conduct experiments. So that's a 96 well, that's a 384 well. And so you can put these on this instrument. This is the plate carriage that they go on, and the instrument will analyze all of those wells. There is a cuvette reader, chamber here as well. So if you are familiar with spectroscopy, you've probably heard of the cuvette, which is just a small piece of quartz, a holder basically where you put your sample in, and so that it has that as well. Most people are familiar with those, and not so much, a plate like I just showed you. But anyway, that's what this thing does, and it measures absorbance. And I can go into a little bit of detail about how these things work. They're all very similar, but I've got the thing open, so I figured I'd show you. Starting with the light source. So lifting up this ribbon cable here, this is the light source. It is a module that has the lamp, which is a xenon flash lamp, and then so that's basically sitting right around here, and then there's a mirror that directs the light this way. It's attached to the high voltage supply, power supply for that lamp. Now, xenon flash lamps, they require a much higher voltage than mains, and it's DC. They usually operate about anywhere from 300 to 1,000 volts DC, and that voltage is usually pulsed at a, depending on the application, different frequencies. This unit can change that pulse depending on what's needed. And so that light from the xenon lamp will come out this way. It'll pass through this filter wheel, which has a few different filters. Could be band pass, low pass, high pass filters. I'm not quite sure. And then it's directed to this, which is a diffraction grating. And so the light coming from this xenon lamp is a huge range. It covers, well, this unit, for example, can operate from 190 to 1,000 nanometers. So that light coming from this lamp has to at least cover that range. And so when it hits this, it's a whole range of wavelengths. And then this diffraction grating will direct the light, it'll diffract it into its individual wavelengths. Based on the angle that the light hits this, you will get different wavelengths. And it's directed into that little hole there, where there is a fiber optic cable, which then goes to the reed head of this instrument, where the light is then directed to that microplate. That's how these work. You can even see, if you're looking at the camera now, you can kind of see how that diffraction going on just from the light in the room, or I'm not sure where that's source of that, but there you go. It kind of looks like a prism. Excuse me. That's how these work. Now, the issue with this instrument, it started with, during the startup of this instrument, it was giving this error. It named it a 401 error, which is a filter wheel error. According to the manual, and I have that pulled up here. Geez, of course that just, yep, good. So this is the manual, and before I get into the error codes, this is the maintenance section, just to give you guys an idea of what I'm talking about. Cleaning the instrument. Replacing the fuses. They have the audacity to tell you how to replace the fuses. If you're replacing a fuse, that means there's something else wrong with the instrument. The fuses just don't go bad for no reason. And then some tips before you move the instrument. That's it. That is all they give you. And then this troubleshooting area, this is just telling you what the error codes are. That is it. They don't give you any real troubleshooting. There's no troubleshooting trees or anything like that. But let me just show you what this filter wheel error is. So here it is. Filter wheel did not move to its photo interrupt in a reasonable time, or cannot find its photo interrupt. Now, when this company says photo interrupt, they are referring to a optic homing sensor. Alright, because you can even see, like, the carriage motion error. Photo interrupt, you see that right there. The carriage, again, that's the plate carriage, where you put the plate. That will also go through, during the startup, it'll go through a homing procedure so that the unit knows where the plate is, where what position it's in. And it knows that via these optical homing sensors. They're usually these U-slotted photo micro sensors, where on one end they have a light emitting diode or an infrared emitting diode, and then on the other end there's a photo transistor that can sense that light. And so if an actuator passes through there and blocks that light, that's how motors, anything with that has some sort of motion of some kind, that's usually what's employed so that the motor can home itself. I see these all the time. So that's what this error is saying for the filter wheel. Now, the problem with that is, this is the filter wheel. There is no homing sensor, okay? There's no homing sensor to be found. Now, this SpectraMax, there's been a lot of generations of this piece of equipment. We actually have one that's a lot older. This is the ABS Plus. I'm showing you a manual now for the M2. It is the exact same. You can see here, filter wheel did not move to its photo interrupt. It's the exact same description. Now, the M2, its filter wheel does have a homing sensor. So, another thing, this company didn't even bother to update their error codes. It looks exactly the same. It looks like I'm just switching between duplicate pages. It's the exact same. They didn't even bother to update their error codes for a more accurate description. So, when I saw that, that threw me for a loop for a bit. Because, yeah. But, because of that, I found out after doing a little bit of research, and I found out that basically means, that error means that the optical alignment has become misaligned. And so I would need to make an adjustment to bring this back into alignment. Now, the way that's done is at the diffraction grating. Alright? You can see on the side there's an adjustment screw. On the bottom there's an adjustment screw. And that is how you adjust the diffraction grating. That is really the only way, the only spot where you can make adjustments. There are some adjustments. If I was to remove this, well, actually, I can show you here. There are set screws as well for the lamp module, but I don't believe that is where, for example, a molecular devices tech would be making adjustments if this goes out of alignment. That's all well and good, but how do you know what to adjust it to? And that's what made this pretty difficult. Now, as I was saying earlier, molecular devices and companies like it will not support customers servicing their equipment. That's their exact words. So they will not provide me a procedure for aligning this. So I was left to figure out how to do that myself. I had a couple clues and some ideas on how to do this. During the startup of power on, the instrument goes through a bit of a initialization process, a bit of a self-calibration, if you will. And so Molecular Devices was nice enough to kind of give some details on that on their website. Here's a couple of descriptions of what happens during that power on. Now, this isn't necessarily specific to this instrument. It's for a variety of their spectrophotometers, but it does seem like a lot of this is applicable to this piece of equipment. So, during the power on self-test, you have the stage and carriage are homed, position is tested. It does do that, so that plate carriage will move. Sorry about that. That plate carriage will, the drawer will open, it'll close, and then it says the DAC is calibrated, gratings and read heads are homed. So again, that diffraction grating has a homing sensor, so it'll spin that around to home that. Lamp strength is verified, and then this is important. This step right here. Accurate grating homing is done by optically locating the zero order from the grating, and then all wavelengths are located relative to the zero order position. Well, what's zero order mean? So you'll have to go back to physics if you took that. I do remember optics from physics vaguely, but fortunately there is Google. And I found this image to best kind of show what the zero order is. Now, if you look here where it says M equals 0, you see this incident light coming in. This is the diffraction grating. you can see the light getting diffracted, and there's different orders of diffraction. So this is the first order, then the second order, and then you have negative values as well. But look at this one, m equals 0. It looks a lot like the incident light. That's because, now, this is how I understand it, but if I'm wrong, please mention in the comments. The 0 order is basically just the light getting reflected. Okay, it's not getting diffracted, so it's not being broken up into its composite wavelengths. And so that's why it doesn't look like a prism like these other ones. And so the instrument is using that 0 order to then determine the accuracy of all of the wavelengths being diffracted. It's using that as a reference. And so that gives you a big clue for calibrating or adjusting this, the diffraction grating. Alright, so when this thing does its power on process, it spins this filter wheel. Well, it'll home this first, and then the lamp will come on briefly, and it'll spin the filter wheel to kind of check that, and then there's one last step it'll do where it'll start moving slowly. You can see the 0 order. I'm going to show this in a second, but you can see that it moves the 0 order light to the where the fiber optic cable is, and then from there it'll kind of move it back and forth. So you can see it doing that self-calibration. So if you find that this is misaligned, you're going to have to make sure that it is getting that 0 order light to the fiber optic cable. And then there's also resolution as well, which is going to play a huge role in where the wavelength falls and wavelength accuracy. So moving this forward is going to lower your resolution. Moving it back is going to increase it. So there's that as well. Excuse me. Alright, so I had a few different clues, and it took me a while to get this right. Another thing that's going to come in handy, you're going to need one of these. Or at least, it's very helpful to have this. This is from the manufacturer. It's called the SpectraTest ABS1 plate. This is basically just a plate with a bunch of optical standards with, it has values for absorbance and also the wavelength accuracy as well. Yeah, I've got one opened up here. This is the most recent one. You can see there's different standards, and then yeah, so this is very helpful to have. You're gonna need that. And another thing that I did want to mention, I'm kind of all over the place here, and I apologize for that, but you'll see that I've got all of these wires all over the place, right? So I wanted a way to keep the lamp on as long as possible, as long as I wanted, because it's only on for a brief period of time during the startup, and obviously when you're running an experiment. You don't have any way in the software of just manually turning the lamp on or off. There's nothing like that here. So I had thought of powering it externally, which didn't work. The instrument wasn't happy with that. But what I did come up with, and this took some measurements, I had this off, taking some measurements on the actual high voltage supply board to figure this out. I found the signal that sends the pulse to this to determine the frequency that this should be pulsed. And I can show you guys that because it might come in handy if you're trying to do this. So if you're looking at the cable like this, you can see, like, for example, there's that little notch right there. So we're looking at it in the same orientation, okay? So 1 is on the right, 25 is on the left. It's a 50-pin cable. The pin that of interest where that pulse is 7T if the top is where that notch is and the bottom is the other side. Okay, so 7T. I actually have, sorry about that, this green cable right here, that is then going on to the orange one. That's the jumper wire that I was disconnecting to then connect it to my pulse generator. And so I can even show you what it's set to now so that you guys, if you're trying to do this, you can do this. So right now the frequency is at 200 hertz. I wouldn't go much higher than that. You can lower it if you need to, but this works fine. The width is 500 milliseconds. I'm sorry, 5 milliseconds. The amplitude is 4 volts. It's really closer to 5 volts, but 4 is fine as well. And then it's offset by 2 volts. So that way it's the when the pulse is, when there's no pulse, you're at ground. It's not dipping below, going into the negative. So yeah, that's what you could use, those parameters, to power this lamp, as long as you want. Another thing that would be come in handy is you could see this button here. It's switch number 1. By pressing that, it will automatically start the instrument's power on self test. So instead of power cycling it and waiting for a bit, you can just do that, because you're going to have to be doing that a lot to get this correct. I'm starting to lose track of where I was. So yeah, that's just a few different things that you can do, or just some details on how you can align one of these. And so let me turn the lights off, and I'll show you it going through its startup procedure, and then I can give you guys a bit more details, and then we'll wrap up. I won't keep this going too long. Okay, so I've got the lights off. I do have my headlamp on just so I can kind of see what I'm doing, but I'm going to press that switch 1 button on the main board, and you guys will see it do its power on self test. So, okay. Okay, so right now it's doing the homing of the plate carriage. And then you can hear it spinning the diffraction grating. Okay, now you see that little blue line? That is the 0 order, and you can see it just barely. It's moving towards the fiber optic. See, now it's about to hit the fiber optic cable. And now it's done. Okay, so that is a successful self-test. Now, you could kind of see how the 0 order started a bit far away to the left of the that hole for the fiber optic cable. I could have made that I could have made that a little bit closer. Initially, I was trying to get this during the adjustment process. I was so close. I was like 3-5 nanometers off of the wavelength accuracy standards, and I thought it was because of the positioning of that 0 order light. And so I started moving it a bit further away, and it didn't change anything. The problem was actually where I had it positioned, the diffraction grating, I had it positioned too far back. As I said earlier, that will have a lot to do with the resolution. And so, because it was too far back, it was making the wavelength a greater value than it should be. And so I can show you guys in a second a few of the runs that I did that'll kind of show this, but when I moved it all the way forward, using that adjustment screw at the top there, right there, then all the wavelengths got smushed, so the resolution got real poor, and it moved them really, it made them much of a lower value than they should be. So that is really important, the adjustment forward and back. Now, one thing I will point out is when it's going through the initial cycling of the filter wheel, if you don't have it positioned properly, okay, it'll stop immediately, and it'll give you this filter wheel error, and that's what it was doing initially. What I would recommend is when this thing homes itself, disconnect, cycle it, pressing that switch, make sure you have pin 7T disconnected, okay? Have it hooked up to your pulse generator, but turn it off. Don't start it yet. Power cycle it, let it go through the initialization. It's gonna fail pretty much immediately because there's gonna be no light coming from the lamp. But what that does is it homes the diffraction grating for you. And then from there you can adjust it the way you'd like. And so you might need to manually move the filter wheel because it might be on a filter that doesn't allow you to see visible light. I would choose the filter that is probably just no filter at all. And what you want to do is position the grating so that you are in the violet region. You're in the violet region of the wavelength of the light. You have the violet region on the hull for the fiber optic cable. Alright? That's what you're going to want to do, and if you do that, you'll notice when it does make it through the cycle to where it puts the zero order light close to the fiber optic cable hull, you'll notice it's slightly to the left of it, and then it'll move it over and it'll finish up the power on self-test. That is what I did, and then with some adjustments to the grating forward and back, I got the wavelength accuracy correct. Alright, so let me just show you a couple more things and then I'll wrap this up. Actually, I figured I would just show you guys real quick just what I was referring to about how to use the pulse generator and to power the lamp at your leisure. So this is what I did. I disconnected the pin 7T, that's just what I'm referring to it now, from the main board, and now you can see that red cable. I have it connected to the pulse generator. The output is disabled currently, but what I'm going to do is I'm going to power cycle it or start the self-test again. Now you want to make sure you can see that's right under there, that's the cuvette reader. If you're directing light at that, it's going to fail automatically for stray light. So that's why I'm covering my headlamp. But watch, it's going to fail automatically. It's homing the diffraction grating because there's no light coming from the lamp. See, the drawer popped out, so it failed, or it errored out. And now I'm going to turn on the pulse generator. Okay, so I enabled the output, and look, the lamp is on, and I want to show you guys, I'm going to turn the lamp so that it's in, yeah, you see where it's kind of hard to see. My camera's doing a weird effect, but this is where I have it positioned. It's pretty much in the violet range area, the range of the spectrum. As you can see, blue to the side. If you put it there, around there, that is going to put the zero order to the left of it. The diffraction grating is going to move that zero order slowly towards the fiber optic cable, and then it's going to be able to perform a reference measurement for all the other wavelengths. If you position it there, that'll put you in a great position to finish the rest of the optical alignment, which, depending on where the diffraction grating is forward and back, it may need some adjustment, and I'm going to show you guys that part next. Alright, so then you can power off your pulse generator, you can reconnect your lamp and that pin, that jumper wire, and it'll then be powered on via the instrument. You might have to do this several times to get this correct, but it's the best that I could come up with without having a procedure from the company. All right, so I'm just going to show you guys one more thing, and then I'll wrap up. Okay, so this will be the last clip of the video. I'm just going to show you guys a couple more things, and then we can be done. But this is, again, you're going to need this this plate, or it's going to make it a lot easier. Now, you can find these on eBay for relatively cheap, for a couple $100. They occasionally show up, and then because from the manufacturer they are a few $1,000s, but you can get it on eBay. Like I said, it's very likely that it'll still be in calibration, but might be a good idea to send it out to them. That's the expensive part. It's almost $2 grand to get it calibrated. We have to do this every year. I actually do it maybe every 2 years. I can, if I time the annual calibration verification just right, I can probably get 2 years out of it. That's normally what I do. But yeah, you're going to need one of these for the wavelength accuracy standards. Without any help from the manufacturer and this, it's going to make doing this very difficult, at least I think. But with that plate, there's one cool thing about this software is it does make doing the calibration verification very easy. So if you go to Protocol Manager in the software, the SoftMax Pro software, if you go down to reader validation plate absorbance, you pick the SpectraMax ABS Plus, if that's what you have. That's what I'm in right now. You can see all of these tests. So these tests, the endpoint and kinetic, those are done with nothing in the drawer, no plate. These other tests, so optical align, ultimate dark, photo accuracy, photo precision, stray light, wavelength precision, and wavelength accuracy, those are the tests you do with the plate. And the one that's going to really come in handy is wavelength accuracy. So if you click that and or highlight it here, it'll just run this test. And so make your adjustments like I showed you, run this test and see what you get, and you'll have to keep repeating this process until you get it dialed in. Now I took some screen grabs of some previous runs just so you guys can get an idea of what I'm talking about. So this, for example, is a passing run for the helium oxide standard, and so it has 3 peaks. This peak here, and then this peak here. All right. So if you move that diffraction grating all the way forward, like I was showing you guys earlier, let's see if I have it. Geez. All right, we'll do the V30 standard, I guess, because I don't have the helium oxide one. All right, so this is the V30 passing. So it's a little bit harder to make out this one, but this is peak number 1, should be about around roughly 330 nanometers. Peak number 2, I believe I have the, yeah, here it is. So yeah, peak number 1 is 330. That's that guy right there. Peak number 2 is a roughly 431. That's this one right here. And then peak number 3 is 681.7. That's that guy right there. Alright? And this is a passing run. They need to be plus or minus 3 nanometers, and that's passing. This is with it all the way moved forward. And you can see the difference. So let me see if I can just kind of switch between them. So look, that's passing, and that's failing, and you can see the difference in the resolution. You can see how all of the peaks were moved forward. So that's peak number 1, where it should be like right around here. That's with this guy moved all the way to the front. Alright, so if you're seeing something like this, or the wavelengths are too low in value, you need to move it back a little bit. And that goes the same for if the values are too high, they're higher than the standard, then you just move it a little bit forward. And with these set screws, you have a lot of control over the adjustment. But yeah, that's pretty much all there is to it. And excuse me, it took me a while to figure that out due to the lack of resources from the manufacturer. But once I got all of that, understood it a bit more, it wasn't too bad. So this actually, after I did do the adjustment, I'm going to show you guys one last thing. Are the results for this run. You can see this was after I adjusted. Everything is passing with one exception. It did fail just barely for stray light. The A7, there's a standard for stray light in each A, B, C, D, E, F, G, H. There's one standard for each. Well, it failed at 250 nanometers. It was at this is the acceptance criteria greater than or equal to 3.15. It's 3.149, which kind of sucks because really, if that's really what that's how many sig figs they give, well, that really is 3.149 is 3.15. But anyway, I think it failed just because this thing is still open, the cover's still off, and I'm pretty confident that once I put it back together, I'm going to have to run it again anyway. It will pass. Alright? But as you can see, wavelength accuracy, it's acceptable, everything else is good. So you can, in closing, you can perform this alignment yourself if you have the right tools, and hopefully with the help of this video, it shouldn't be too bad. Fortunately, these rarely do go out of alignment, but let's say your company is looking to purchase one used, or for some reason yours goes out of alignment. You got to be careful where you place these. Don't put them near anything that vibrates a lot, like a big heavy centrifuge or something. Try not to move it around too much, but for whatever reason, if yours falls out of alignment, you get this 401 error, you can do this yourself. Because Molecular Devices, we got this thing for roughly $15,000 new. It probably would have cost us half that just to repair this, just to perform this procedure. So, and that's why I'm sharing it with you guys, because it's ridiculous. You know, that's one of the reasons why I made this channel, was to share this kind of stuff with others, because of the limited resources that these companies provide. But anyway, gone on long enough. I'm going to stop this here. I hope you guys found this interesting. If you do know how to do this alignment the right way, and you want to share it with me, by all means. If you have any other comments, please leave them in the comments below. And yeah, I hope you guys found it interesting, and I'll catch you guys next time. Alright.